is dissolving. And I'm guessing you're thinking, you know what would be really great would be a lecture on what dissolves things, and you're in luck. Today is that day. Now, here's all my life. So most of us understand that if we throw certain things into water, they'll dissolve, and other things not so much. I do remember when I was growing up, taking dirt, throwing it into a cup, stirring it really, really vigorously, handing it to my younger sister saying, chocolate milk. And it worked once, and then she trusted me never again for the entirety of my existence all the way through now. She still doesn't trust me. So now that wasn't that clever, because if you've ever messed around with dirt, it is not something that dissolves in water. Now, there's a number of liquids we could dissolve things in, but let me define some terminologies for you first. So first off, whatever's being dissolved, we call the solute. So the solute is what is being dissolved. You don't need to write it on the board. You should probably write in your notes. This is going to be kind of like the verbal portion of the lecture. Solute is what's being dissolved. Solvent is what's doing the dissolving. Solute's what's being dissolved. Solvent is what's doing the dissolving. Now, the solvent we're going to be using for the entirety of this lecture is going to be water. So water, and sometimes they refer to water as the universal solvent. That's just a fun fact that you may never need to hear again or see again. But water dissolves a lot of stuff. And in fact, because water is able to dissolve things, it allows ions from different things to come together and react. So we use water to actually cause a lot of reactions, because water allows ions to break free and form each other. You guys remember when we did double replacements instead of a compound and a compound? Well, if I have two compounds that are just solid rocks of compound and I bring them together, they're gonna be like, ugh, right? But if I throw them into water and the ions break apart because they dissolve, now aren't the ions free to move around and interact with each other? In fact, we consider water to be like the dance floor where all the individual ions hook up. Now, so you understand, not everything dissolves. And you guys probably understand this is in general. I mean, what's something that you on your own have thrown into water and seen it dissolve? Salt. That's a typical example. And who doesn't enjoy a good swig of salt water? Yeah. But let's take salt, for example. Side note here, we use the word salt to describe NaCl. But from here on out, you should understand that salt is actually a generic term that refers to all ionic compounds. So if any ionic compound from here on out, we're going to call it a salt. So just be aware of that. All ionic compounds are known as salts. So if I say we're going to throw a salt into water, don't be like, oh, NaCl. It could be anything. MgNO3, parentheses 2, BAI2. I could go on for as many ions as I know, right? These are all salts. Now, when you throw that salt in the water, as Randall often does, yeah, when we throw that salt in the water, we typically stir it or crush it up or whatever to make it dissolve a little more quickly. But as if by magic, when we stir it around, doesn't it disappear? Yeah. One of the things about dissolving or something forming a solution is that both the solute and the solvent enter the same phase. So if you have a solid as your solute and you have a liquid as your solvent, if they dissolve, if they are dissolving in each other, then you're only going to see the liquid phase when you're done. That kind of makes sense? Now, let's say you are overambitious with the salt, Randall, right? So you're like, salt is my life, right? And you just pour in and stir, pour in salt and stir. What's eventually going to happen? That's true. But let's pretend that there's still more water than salt. But isn't there a point, a saturation point where the water's like, nope, not going to take any more salt. And as much as you put in there, it'll just sit out of solution. Are you with me? Salt is a bad example. I like to refer to my earlier days with sugar and or particularly brown sugar or chocolate powder in milk. Back in the old days, we had Nestle Quick, which was the chocolate powder before we had like all the squirty things. And when my mom, and I think I shared this before, but my mom gave us the Nestle Quick, it was the tip of a teaspoon, no joke, in a whole thing of milk, and it barely even made the thing a slightly brownish hue. When I went at it, aka she was nowhere around, and I knew where the Nestle Quick was, I would liberally put in the Nestle Quick. Stirring occasionally, but not that concerned, because as far as I thought, the slurry at the bottom was the best part. So I started going to like a sugar coma afterwards. But if I'm pouring in and stirring, pouring and stirring, eventually you reach a saturation point where the water or liquid of any kind says, done. I've had it up to here with you. Probably heard that expression, some of you, by your parents. I don't know why when they talk to me, they always are like, I've had it up to here, and they reached very high up on their bodies. It was never like I've had it up to here and they reached down low. Usually they'd had their fill. This is exactly how water and solvents are. Solvent will say, you know what? I'll take this many ions of Na and Cl. But you put any more in, nope, I'm not going to allow you in. You're going to sit there by yourself. Think about what you did. Are you with me so far? Now,
what is it called when you can't take it anymore?
It's saturated. The solution is saturated. Now, we'll come back. We'll revisit this in a little bit. But let me show you a little diagram of how dissolving actually works. And I want you to write one statement here. And this is the principle behind which we, oh, that's a lot of things going on.
We've reached Nirvana.
you guys are so silly. But I guess that is the correct response. Ready? So I'm going to make one statement here, and this is going to be kind of our guiding principle. Here it is. Like dissolves like. Like dissolves like. What that means is polar dissolves polar. Nonpolar dissolves nonpolar. Like dissolves like. Polar dissolves polar, and nonpolar dissolves nonpolar. Now, let me point out something to you here. You guys should be able to see on my screen a water molecule, yes? Is it broadcasting to all of you right now? Okay, so if you take a look at this right now, water molecules are polar. Now, if you remember, if we were drawing dipole arrows, let's say that was a section, see how the hydrogen electrons in the hydrogen-oxygen bond would shift towards the oxygen in both cases, and it would make this partially negative and each of the hydrogens partially positive. That makes a polar molecule. Agreed? Now, what we know is that polar things dissolve in polar solvents. So polar solutes dissolve in polar solvents. Now, let's just pretend that I had any ionic compound. Do you realize that every single ionic compound is always a positive ion and a negative ion put together? And typically, when you have a positive ion and negative ion, they get put together in these large lattice structures, right? And the reason they put them in those large lattice structures is that it's more stable for them to have a bunch of them hugging onto each other than just two of them hugging onto each other by themselves. So think about this for a second. Isn't an ionic bond the most polar you can ever have because you have a full positive and a full negative? So wouldn't it make sense that ionic compounds should dissolve in water because ionic compounds are way polar and water is polar? So if we take a look at how this actually happens, let's take a look at this particular structure. Now, this is an example of water molecules interacting with a salt. Notice how we use the word salt in the generic term. That, if you take a look here, we have fat old negatives and little tinier positives here. This could be any ionic compound which has a positive and negatives in a lattice structure. So what actually happens with dissolving is this. These water molecules, do you see how they arrange themselves so that their negative end, see the little, can you guys see my pointer on the screen? The negative end will interact with the positive end on the actual ionic compound and try and pull it off. Now, here's the thing. This positive has to want to go. And the water molecules have to provide it with stability that is enticing to it. So if this water molecule walks up on this plus, the water molecule, particularly the O minus, will be like, how you doing, right? And the positives will be like, oh, I'm not gonna do this anymore. I feel embarrassed, and I also just realized I'm having this now on video. So we're just gonna end that exactly right now. But it's not just one water molecule. Many other water molecules are like, hey, it's so great over here in the water. That's all I got. And the positive ends up leaving. And if you take a look, the water molecules are like, nom, 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 right? They kind of all surround the positive, and the positive is all like, oh, kumbaya circle, right? And simultaneously, if you take a look at the water molecules' positive ends, which would be the H pluses, do you see how they go after the minus? and they're like, hey, come with us because it's super great. And this happens over here. Yes, ma'am.
So will it always be the negative part of the solvent trying to pull apart the positive part of the solvent?
Always. Always. And it makes sense, right? Because don't opposites attract? So, and by the way, it doesn't even have to be, if you look at the water molecules, it's not even a full negative, right? It's a partial negative because electrons are just shifted. But they have so many water molecules per ion that they actually have a pretty strong pull on the ionic compound. So over time, what ends up happening is the water molecules just simply pull one by one. You see how this guy over here is getting ready to pull, these two are getting ready to pull this one off. They pull until they remove all the ions that they can, and or they reach the saturation point of their liquid. So if I put too many ions in there, the water is going to be like, I can't handle all this. The other thing was interesting, and I think you guys need to be aware of this, and I shared this briefly at the beginning, is that when something dissolves in something else, it assumes the same phase or state that it dissolved in. So if I have water, that's a liquid, right? And I have these ions, when they get pulled off, they assume the phase of the water. Now, I never really grasped how this was. I always kind of thought like the water molecules were covering it, so we just couldn't see it. But in reality, think about this. How small is an individual ion? Incredibly. Like, just to give you perspective, a single crystal is trillions upon trillions upon trillions of ions. Like a salt crystal, like this, the smallest little grain of salt that you have, that is a single, lattice structure, but there are trillions and trillions of ions. If I were to pull one of those ions off, are we seeing that ion? Not at all, right? So the reality is that we just don't have the ability with a naked eye to see these ions floating around. So it appears that they're hidden in the solution, right? But they really are just too tiny to see by themselves. Are you with me? Now, here's the problem, as there often is, because I can't pose you a general rule without going, oh, by the way, here are exceptions. So we say that like dissolves like, right? And that is a true. So that's a truth, right? Like dissolves like. Polar things dissolve polar. But I'm here to, unfortunately, tell you that not all ionic compounds will dissolve in water. So this ionic compound that you're seeing on your screen right here to the left, it could be like, nah, don't want to go. Now, why might that happen? Well, what if you have a good thing going already? Like these positive and negatives you look on your screen, I mean, they've been through a lot together. Maybe the positive and negatives are so stable in that particular ionic compound, when the water comes up as like, come hither, the ions are like, no, I don't want to. I'm going to stay where I'm at. So if the ions are actually more stable staying in the ionic compound in the lattice structure, then even though it's polar, it won't dissolve. This puts a kink in things for us because I like rules that are all-inclusive. Polar dissolves polar. Done. But we know that polar dissolves polar, except sometimes. And so in order to determine when that is, I'll get you in just a second. In order to determine when that is, we're going to learn solubility rules. Some rules that let us know when is that ionic compound actually going to dissolve and when is it not. Are you with me? Yes.
So, with the stability of the compound, that related at all to the reactivity of atoms?
Absolutely. Absolutely. And more importantly, though, the charges of the ions and the size of the ions. The smaller, do you guys realize it in a weird way in chemistry world, it's better to be smaller? I don't understand this concept because I always was like big is better, right? We're in Texas. But if you look at ions, if the ions are smaller, do you realize they can hold on to each other more tightly? And if you hold on to things more tightly, then when water comes to try and pull you off, you're gonna be like, hey, we're really stable. Or if the charges are bigger, do you realize that a +1 and a -1 will not hold as tightly as a +2 and a -2? They're just bigger charges, they'll hold more tightly. So there is a direct relationship, by the way, Leo, to the periodic table and where things are. That is beyond the scope of what I'm covering right now. What we're gonna do is we're gonna look at some rules. Now, I will say this, when I first approached doing these rules, it was, so I'll tell you. I went to a chemistry conference Yeah, I know. I went to a chemistry conference, and in that conference, we were talking. No. In that conference, one of the things that came up were solubility rules. And the unfortunate truth is if you look up the solubility rules in your textbook or anywhere else, they're pretty confusing. You just have to memorize a bunch of things. So we sat down, and we were actually in the Bay Area in California, and over one of our breaks, this other teacher and myself, we came up with these solubility rules, and we were like, these are the greatest things that have ever existed. In fact, we used the acronym SAWS, S-A-W-S, and then each of those letters represented a different type of compound, and then there were rules that follow. And so I used SAWS for a couple of years until one of my students, I asked them to try and to put put their own little page together of all the rules, and she took my SAWS rules and came up with ABCD. And her rules are so much better than mine were in terms of like, she used all of my rules, but she organized them in such a better way. Her name was Sam Nordland. I always reference her because I still use her stuff to this day. And the reason that ABCD is so great is because it's alphabetical first, right? I don't want to like your brain or anything, but ABCD is alphabetical, but it also means this. You have to follow each one of these represents a rule, A, B, C, and D. And because they're sequential, you cannot apply rule B unless rule A does not apply. And rule C cannot apply unless you've already tried to apply B and A and they don't apply. That's what's so great about her rules is that mine were not in sequential order. And so it left questions about like, what if there's two rules that it can apply? Which one do I apply first? A, B, C, D takes care of that for us. So in short, what we're gonna do right now is I'm gonna teach you four different sequences of how we deal with ionic compounds and whether or not they are soluble or not. And the first one is A. Now, A stands for strong acids, hence the letter A. And what you should know about acids is that every one of them has an H in them. Now, see at the top of the page here where it says CBS PIN? That's an acronym for the 6 strong acids that exist, and there are only 6 of them. Hydrochloric, hydrobromic, sulfuric, perchloric, hydroiodic, and nitric. And you see how I've highlighted in blue where we get the letters from CBS PIN? I want you to write all of those 6. And the rules that I'm giving you right now are for what are soluble, able to be dissolved all the time. Now on the board, would you do me a favor here, Leo? Could you write an HCl with an arrow near the top? And then underneath that, could you write HNO3 and an arrow? Give some space. HNO3 and an arrow. Okay, and then I want you to write HF and an arrow. Okay, you guys all written down the rules?
You said able to be dissolved all the time.
Yeah, so see where it says soluble with 2 exclamation points? Soluble means if you ever have HCl and you throw into water, it will 100% dissolve. It'll break apart. HNO3. These are the only 6 that are part of the A rule. Always. Now, what I'm going to do here is I'm going to turn to you here. So let's make sure that you're on this, Leo, that you are able to be as focused on. In just a minute. Okay. Can you guys all see what's on his screen right now? Okay. So watch. I'm going to use 3 or 4 terms that all mean the same thing. You ready? HCl is soluble. HCl is able to be dissolved. HCl can dissociate completely. HCl can break apart 100%. All these words, dissociate, break apart, become soluble, become ions, all these mean they break apart. So what we have is this. Acids have H's. So if we ever have a compound right now that has an H in the front of it, we are going to have to apply the A rule. And the A rule is this. If you have a strong acid, you are soluble. If you have any other acid other than the strong acids, you are insoluble. Insoluble means you cannot dissolve. So the CBS PIN are the only 6 acids, and the acronym is supposed to help you with that, the only 6 acids that actually 100% dissociate, aka 100% dissolve. So taking a look up here at the HCl, if we have HCl and we throw it into water, it will 100% break apart into H plus Cl minus. That means there's going to be none of the HCl left undissolved. Now, we're not talking about oversaturating a solution, though, right? We're just talking about putting in up to the saturation point. Now, let's look at HNO3. If we're doing if you're looking at your A rules, isn't HNO3 nitric acid isn't it one of the 6 strong acids? Yeah. And by default, the 6 strong acids they 100% dissociate. So we're going to end up with H plus and NO3 minus. Now let's look at HF. Indeed, indeed. Is HF an acid? Yes. Right, because it has a hydrogen in the front. Is it a strong acid? No, because if you take a look at CBS pin, F is not part of CBS pin. HF, agree? So what we're going to write next to that is insoluble. Insoluble means it doesn't dissolve. Now, here I want to speak truth to you here, because when I say insoluble, I don't mean 100% insoluble. Some of the ions may go into solution, but the majority of them will stay as HF. Like under 5% will leave. 95% will stay as HF. Now, do me a favor here. Can you draw like a beaker to the right-hand side? A beaker, like to the right. So make it be perfect. Circle the top. Finish the top, man.
Is that basil?
Okay, and then make another one. Make another one right next to it.
Is that Baku gone forward?
Stop with the chippering at him.
Sorry.
Oh, I like how you're drawing. I mean, I assume you like the second one more. Is that why you made it taller? Don't, leave it. Okay, in the first container, I want you to put H plus near the top and Cl minus somewhere down to the right on the bottom. So watch, and this is actually more, man, it's hard to see that. Maybe like a different color or maybe make it a little bit bigger because the people that are watching the video are gonna have a hard time. Maybe use the green maybe. Oh yeah. Woo. All kinds of Christmassiness. Okay. What mostly is going to happen in our problems is this. We're not going to just give you HCl and go, hey, is it soluble or is it not? Because if we do, you're going to be like, oh, yeah, it'll break apart. What we'll do is we'll give you the individual ions and say, will they stay soluble or will they form a precipitate? Precipitate is another way of saying comes out of solution. Can you put your finger on H and another finger on Cl simultaneously? Well, do 2 fingers and I want you to bring them together. Okay. So you have H plus and Cl minus. So let's say I took H plus and Cl minus and threw them into water together. As they're floating around, and by the way, we're not just throwing 2 in there. You guys would be throwing trillions of them in there. Aren't the H plus and Cl minus going to come in contact, come together? So I just want to say that I appreciate how you made the H plus take a somewhat circuitous route to meeting up. Yeah. So when they meet up, they're always going to go back to the solubility rules to do a check. So H and Cl. Move them together. We're going to look at the rules. What is the rule for HCl? Is that soluble or is that insoluble? It's soluble. Soluble means not only when we have HCl as a solid on the outside and we throw it in, it'll break apart. It means if we have H plus and Cl minus as ions and they encounter each other, they won't form a solid. They will continue soluble. Does that make sense to you here? If something is soluble, the individual ions, when they interact with each other, they will stay dissolved. Now, could you write H plus and F minus in the next container? Same exact way, same exact positioning. Okay. In this case, again, won't the H plus and F minus interact with each other? Mm-hmm. But when they interact with each other, now we look at the acid rules. And we know this is an acid because of the hydrogen in the front. Is F minus part of CBS pin?
She is.
Not so. Are you guys all with me? Not so much. What does that mean? That means that it is insoluble, and that means that it will actually form HF. Can you put the 2 of them together, like arrow in, and then just write HF in the middle? Are you following what I just did there?
No.
Okay, ask a question. What don't you see?
Okay, so because it's insoluble, they're gonna come together.
So insoluble means that they don't dissolve in water. Soluble means they do dissolve in water.
So we're pretending we're just dropping like.
So what we're doing is we're doing this. We're taking H plus from some source. We have a can of H pluses. And we're taking a can of F minuses. And we're pouring them both in together. And when they hit each other, they do a solubility check. And when they do the solubility check, they look at the rules. And we're like, hey, we're an acid, right? And we're like, yeah, we're an acid. Let's take a look at the A rules. And the A rule says only CBS pin are soluble. So if I have H, and let's say on the left-hand side, so you had Cl. Cl is part of CBS pin. So when H plus and Cl minus come together, they're like, oh yeah, we're soluble. We can't hook up because we're dissolved. That's what soluble means. But if you look at H and F, F is not part of what is soluble with acids. So therefore the H and the F, they will form a solid, or they'll form a precipitate, or they'll be insoluble. Those are all meaning the same thing. Any questions here? That, by the way, you've just written your first net ionic equation. Because what a net ionic equation is two ions forming a compound that are individually liquid. By the way, remember the lab that we did? You had two, do you remember you had two liquids? And you poured them together and a solid popped out?
Yes.
Well, that's because we had two sets of ions. So this is kind of what we did. Were you here for the lab, Bowman? Were you here for the lab?
Yeah.
So remember, we took two liquids, essentially what they were two ion containers. We poured them in together, and the two ions, they did a solubility check, and they were like, wait, we're insoluble, and they came out a solution. Are you following? So that's what we're trying to do in this section. We're trying to see which ions, when we put them together, are insoluble. We're actually on the lookout for insoluble. The rules are going to tell you what things are soluble. We're looking for things that are outside of those rules. Yes, ma'am. Okay, let's move on. So I'm going to briefly put back up the HCl thing, and we're going to on the other side of the boxes to the right hand side. We're going to do the next section. You might want to move your thing over. So I'm going to share. You're going to see this horribleness. I apologize, but also it is. Thank you for connecting with that. It's super great. Okay, so this is where we were. Just really quickly, let me remind you again. And CBS PIN, it's probably a very, if you can find a different acronym that's better than CBS PIN, have at it. But yeah, I thought of CBS as the television network, and then PIN is, PIN. But it is kind of, the blues are what make the acronym. So here's what you need to know about A. Whenever you have a compound that I give you, I'm like, hey, look at this compound and evaluate it. The first question you're going to ask is there a hydrogen in it? And if there is a hydrogen in the compound, you're going to follow the A rule. Let's go to the B rule. B rule is, do we have a strong base? I have the PowerPoint is, I put it onto your online for you, so you can go back to it if you want to. That was so sad. I felt nostalgic there because my son always goes, oh no, oh no. Yeah, so thank you. So bases have OH minuses in them. Now, the acronym that we're going to use is something called one strong cal bar. And what that means is anything in group one, strontium, calcium, or barium, any of those, when you have them with an OH minus, they are soluble. Now, do me a favor on the other side of the box. Can you write NaOH and an arrow?
NaOH.
So NaOH and an arrow. And then can you write CaOH in parentheses 2 and an arrow? And then can you write AgOH in an arrow? Okay. And can you put an arrow towards the Na on the top? And could you write like there? And can you write up above it? Can you write Li, Na, K, Rb, CS, and Fr? Okay. You guys written down what's on the page? So again, if you ever have any of these in front of a hydroxide, so if you have anything in group 1, now really quickly, isn't group 1 the first column on the periodic table?
Yes.
Starting all the way up at lithium and going all the way down to francium. Hydrogen is not included because hydrogen is actually an acid starter, right? And then strontium, calcium, and barium. So let's go back to the board here real quick.
Wow.
Are we gonna do that every time?
I hope so.
Wow.
All right, let's look at NaOH. So put your finger on the NaOH, please, for me. All right, so if you were to have this sitting on the page looking at you and you're like, huh, is that soluble or is that insoluble? You literally are going to do this, and it may seem stupid right now, but just bear with me. You're going to go, huh, let's look at the A rule first. We're always going to do A, B, C, D. Is there an H plus in this? No. The B rule is there an OH minus? And in this case, the answer to that is yes, there's an OH minus. And since there's an OH minus, we're going to follow the B rule. And the B rule says this. If you have whatever's in front, can you underline the Na and underline the Ca and underline the Ag? If whatever you have in front of that is part of group 1, and I've listed all of group 1 up above it, a group 1 cation. So see how you have lithium, sodium, potassium? I just read the list there. If any of those are with OH, it will always be soluble. Yeah? Also, so that means this. If I have NaOH, is an Na part of group 1? So wouldn't that break apart 100% into Na plus and OH minus? But also we have calcium, silver, and if I take a look at what was the acronym that I gave you for
Strong one caliber.
one strong Calbert? So group 1 stands for anything in group 1. Strong Calbert. Now, really quickly, I was clever this way, but one strong Calbert. Strong stands for strontium, Cal stands for calcium, and Bar stands for barium. If you're wondering how I got that, you realize a lot of my examples from the West Coast. So when I was teaching this at this particular time, University of California, Berkeley, their mascot is the bear. And shockingly, when I was actually creating this lesson a bunch of years back, their football team was ranked #1 in the country. It only lasted for like 3 weeks, but they were #1 in the country. And so this is how I came up with the acronym. So they were #1, so 1 strong Calbert. So they're all, the Calberts are really strong.
Yeah.
So that should help you remember what ions are soluble. Every other ion you put with OH minus, besides group 1, and then strong Calbert, will all be insoluble. And to be honest, we kind of want insoluble. So let's take a look at AgOH. Would you acknowledge that Ag is not part of group 1? It has a 1+ charge, make no mistake, but that does not mean it's part of group 1. Do you understand the difference here? Yeah? So it's a +1, but it's not a group 1. So is it part of cal, strong, bar? No, it's not calcium, strontium, and barium. Therefore, that's going to be insoluble. Can you write insoluble next to it? The one right above it, isn't calcium part of 1 strong Calbert?
Yes.
So in that case, we'd have Ca2+, and we'd have 2 OH minuses. I just want to make it balanced, but if you just want to put OH minus, I don't really care. So let's go back to our 2 containers, please. And instead of H plus and Cl minus, can you put Na plus and OH minus in the same exact spots? And then the other one, can you put Ag plus and OH minus? And then the other container, put what's that? No, Ag plus and OH minus. Okay, so what we care about more is what if we dump ions in together? So put your finger on sodium, put your finger on hydroxide. Okay, we bring them together, Okay, we're going to do a solubility check. And when we do the solubility check, we're like, oh yeah, that's an OH. We have to follow the B rules. And the B rules are, is Na part of group 1 or cal, strong, bar? And isn't it part of group 1? Yeah. So that means that it's soluble, which means nothing will happen. Boo. Let's go over to Ag plus and OH minus. In this case, again, we have to follow the one strong Cal Bear. Is Ag plus part of group 1 or Cal strong Bear?
No.
So that means, therefore, that it is going to be insoluble, which, hooray, that means they're actually going to hook up. So they're going to come together, and they're actually going to form AgOH.
So insoluble.
We like insoluble. We're looking for things that are going to be insoluble.
Otherwise, you'll have no idea.
If not, they're just going to float around, and nothing will ever hook up, and you never see something come out of solution. So we want to see things that when we put the ions in individually, when they hook up with each other, they're like, oh, they do a solubility check, and they're like, oh, wait, we can't be soluble anymore because we're insoluble. Together, we come out of solution. Any questions on this? So we've done A. Oh, anything with an H plus, we follow the A rule. We've done B. Anything with an OH minus, we do the B rule. And now we're going to do the C rule.
Wait, so you would use the insoluble ones, oh my gosh, to create something else? Like,
Whenever we have two ions that together are insoluble, we have to write what the compound is that they will be.
like a reaction.
And that's yeah. So see how we just wrote? See how we put what we'd actually do in this case on the right? We would actually go Ag plus OH minus goes to AgOH. We just take the ions on the left hand side and then show what they form on the right hand side.
Okay.
Now,
So like if you got a problem on a test, it would be like Ag plus OH.
Yeah,
instead of
yes.
AgOH.
yes, or it could go both ways. If I could ask you, is this soluble, and give you AgOH, and you're saying no, it's insoluble, or I could give you Ag plus and OH minus and say what happens, and you go, oh, it forms AgOH. Just hold on, wait till I get to the rules, and I'll show you exactly how we're going to do these. All right, so the C rule actually comes in two parts. This is part 1, and part 1 is nag-sag. And the reason I came up with an acronym is like someone's nagging you, like nag, 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 and you're like, so you sag. Now, the first portion of that represent 3 polyatomic or regular ions. Can you do me a favor? Write down the let's go to the left-hand side where you had the HCl. Yes, erase everything there to the left of the containers. And can you put, watch, it's going to be a little bit tricky. I want you to write NO3 down. Look at Emilio for a second. NO3, and in front of it, put like a little line where we're going to put another ion in front of it. Wonderful. And then underneath that, I want you to put NH4 plus, but you put NH4 plus in the beginning and put another line after it. And then I want you to write well, just hold on for this right now. Can you write NH4 plus and can you write NO3 minus, please, for me? Okay. So really quickly, and for group 1, can we do this at the very bottom? Can you make write all of the group 1 starting from lithium to sodium on the side? Make like a parentheses. So like go like lithium all the way down to francium. Do a parentheses and then put a line next to it. So you guys have that right now. I'm going to go back to him on the main screen. Enjoy the fun repeatingness here for just a second.
Whoa. We're going to reach the flying spaghetti monster.
Yeah. Spaghetti monster, spaghetti monster, believe it.
All right. And can you put a plus next to each one of those, Li plus, Na plus? Okay. Now, ready? So NAG, the NAG portion of SAG, these are compounds that have no exceptions. If you put anything in front of NO3, it does not matter what it is, it will always be soluble. It does not matter what you put in there. So for example, let's put an put an Ag plus in front of there. So Ag plus, right? Now, if you're writing the compound, wouldn't it really be AgNO3?
Yeah.
But because the Ag's in front of the NO3, it automatically will be soluble because everything with NO3 is soluble. Are you guys all with me on this? So nitrates are always soluble. There is nothing you can put in front of a nitrate that will make it insoluble. Yes. Even a noble gas. Although you wouldn't put a noble gas because isn't that a negatively charged? It would. Yes, you wouldn't put a non-metal, but yeah.
So this isn't nitrate itself is soluble, but compounds with it.
So yeah, what we're doing is we're saying, what happens if we put something together with nitrate? Because if I throw nitrate into water, it's just going to float around, dissolve, right? But then if we put in anything else, like Ag+, they're going to come in contact with each other. And when they do, they're going to do a solubility check, and nitrate's going to be like, sorry, man, I can't hook up with anything. So automatically, anything with NO3, you're going to have soluble. It will never hook up with anything.
NO3 itself.
Well, NO3 by itself is just a single particle. If you have a single particle, you're by definition dissolved because you can't break up. NO3- can't break up any, so it just floats around. Let's take a look at NH4+. Similarly, it does not matter what we put on the end of ammonia. Remember, ammonium is the one weird kind of polyatomic ion we did before? Yeah. So if we put a Cl-, let's say after that. And by the way, do you realize I could put every single negative ion that I can think of after that? Every single time we're like, nope, soluble, oxalate, nitrate, acetate. It doesn't matter. If I put something on the end of that, it will 100% always be soluble. True story? True. Any questions? What I like about NAG is that NAG is 100% soluble all the time. So now let's take a look at group 1. So the G represents group 1 cations. So those are all of group 1 as an ion. So from lithium all the way down to francium. If you put them in front of anything, soluble. It does not matter what the tail end of that is going to be. Pick a polyatomic ion you want to put on the end of that. Not a monatomic, polyatomic, one from your polyatomic.
S2O4 or S2O.
SO3 thiosulfate? Yeah, why not? Let's go S2O3 2-. You know what you're going to do? Soluble. It does not matter what we put in there. Let's pick Li. That's still going to be Li plus and S2O3 2-. Are you with me? So every single thing that tries to come up with NAG, nitrates, ammonium, or anything in group 1, we're just going to go soluble. They're never going to hook up. And if you were to bring, let's say, put your finger on lithium and put your finger on thiosulfate. Okay, put them on the other side. Let's say that we put those in individually into a container. When they hook up with each other, when they bump into each other, they're going to do a solubility check. And you know what the solubility check is going to say?
Soluble.
Soluble. Sorry, we can't form or precipitate. We're just going to float around forever. Yeah.
Have to put the charges in the equation.
If they're by themselves as ions, yes. If they're part of the compound, we don't put the ions in there, the charges anymore.
But we didn't have to react.
Correct. And this is a very specific type of reaction that we're working with where the compounds break apart into ions because they're ionic compounds. Any questions on these right here? So, as I waited no time for an answer. So with NAG is 100% soluble. When we look at SAG, okay, and I'm scared that mine might just die here. All right, let's look at SAG portion of this. And this is SAG. Sulfates, acetates, and group 7. Now, the exceptions, here's where SAG has exceptions. So SA and G are soluble, but each one of them has some exceptions. So make sure you write next to, under sulfate, that they are insoluble, or the exceptions to solubility is if they're with calcium, barium, strontium, or lead. And then for group 7, if it's with Pb, Hg2+, or Ag+. Now, everyone look at your computer screen, if you would. I'm going to kind of point this out to you on the screen. Can you do me a favor? On the right-hand side, can you erase and can you put a line in front of SO4 2-? Can you put a line in front of C2H3O2-?
Just break everything while you're at
It
it.
is not broken.
So can I tell you the truth? So I'm a somewhat sarcastic person. I enjoy that. And when I first started, like especially when I was in college, I was very sarcastic. And I started teaching right out of college. And I realized that I had to stop because I was really funny, but I would just eviscerate students like left and right. I'm like, oh, that I can't do that anymore. I'm like, I enjoy it, but I don't think it's right. Anyway, so let's take a look here. Sulfate is SO4 2-. It is a negative ion, so it won't always go at the back.
Yes.
If I put anything in front of a sulfate, it will be soluble, except if I put these four things in front of the sulfate: Ca2+, Ba2+, Sr2+, or Pb2+. Now, here's the acronym that I use to remember this. Cal Bears stir peanut butter. Cal Bears stir peanut butter. Oh, I love that. Leo, you jumped ahead. You totally redeemed breaking my stuff.
It's not.
Just kidding. Okay. Now, you may be thinking that is the dumbest acronym I've ever heard, and I'll acknowledge that is probably true. But let me tell you how I got to this. Cal Bears stir peanut butter.
Yeah, they do.
Cal Bears stir peanut butter. Now, again, you need to understand where this was done. I was doing this somewhat close to where the California Berkeley campus is. Any you guys ever been to the Bay Area in California? San Francisco or whatever? Can you de-hood for me, please? And you ever ventured on to anywhere near where the Berkeley campus is? Okay, have you walked on the Berkeley campus? That is a treat because it's like where all hippies go all the time. Like if you walk like 5 steps and you don't see a hacky sack group, or if you don't see a drum circle, you're like, where am I? Like that's like your center if you're there. One of my best friends growing up, I went to college down in Los Angeles area. He stayed up and went to Berkeley, and he said it was completely common to have like someone totally naked just walk into their class because they were protesting something and just sit there the entire lecture. They didn't even like pay a second attention to it. They're like, all right, I guess I don't know what naked protest actually does, but I mean it was. He shared with me like stories that would happen. I'm like, you got to be kidding me. So pretty hippie-esque place. Like there's like a Whole Foods on every corner,
That's so cool.
right? And so here's how I came up with this. So the Cal Bears are like, they're California Berkeley Bears are really, really like hippie-esque. And so if they ever bought peanut butter to eat it, they wouldn't get regular peanut butter. I didn't know this existed until horrifyingly my wife decided to show me this. You guys realize that the peanut butter you can get from like, and she just did it this year. I'm like, what the heck, man? You have oil on the top and all the peanut butter mixtures on the bottom. In order to actually eat it, you got to stir it all the way in. And if you let it sit for a while, like a long period of time, it kind of settles back out. And here's the great part about it. It's wretched. It's like the worst peanut butter you could ever eat. That's what, see? Hippie! I call hippie them on you. Anyway, so, yeah. So, like, I do understand, of course, that Jif and like Skippy have inordinate amounts of sugar to make it sweet. But I also realize that I like sugar, hence this. But this peanut butter is stirrable, right? So how I remember this is sulfates, they are soluble, always. But if you put Cal Bears stirring peanut butter together, calcium, barium, stirring, strontium, peanut butter, Pb for lead, you end up with an insoluble thing. Are you with me? Yeah. So everything with strontium, I'm not going to bother doing this, but I just want to point this out to you. I could put anything in front of strontium or anything in front of sulfate except for Cal Bears stir peanut butter. I'm going to go back to the board here. And they would be soluble. Another dimension. Okay. Now, if, however, you see a Ca2+ in front of the SO4 2-, can you put a Ca2+? Now, this is not actually good form because, Kenny, you asked this before. If I actually have Ca2+ and SO4 2-, aren't they the same ion? Wouldn't they just be CaSO4? But I'm just showing you which one we could put in there. But CaSO4, that is insoluble, right? Yeah. Because only Cal Bears stir peanut butter is insoluble. So therefore, it would form CaSO4. We say that is insoluble, right? Let's look at acetate. Now, here's the problem with acetate. Do you see how there's no exceptions for acetate? Yeah. So acetate no matter what you put in front of it, will always be soluble. Now, I had wanted to make my NAG all soluble and my SAG soluble with exceptions, but I had acetate to work with. I didn't know what to do, so I temporarily made it NAGA-SK, like NAGA for the first one, and then SK, which is the totally the dumbest thing ever. So if you can, if you can think of a way like to make NAGA into an acronym by itself and SG into an acronym by itself, NAGA is all soluble without any exceptions, and SG is soluble with exceptions. However you want to do it. This is so dumb because at the time I was playing a video game and Nagas were actually a creature name. So I was like, Naga, that's great. Everyone, and I'm like, oh, no one is going to know what a Naga is. Anyway, acetate, they are 100% soluble. Put anything in front of it you want.
Does it have to be positive?
Yes.
Yeah.
He asked a really good question. Can you ever put two negatives together?
No.
Two negatives do not.
They do not. Oh, good. Or two positives. Two positives can't go together either. What did you put in there?
What if we put?
Oh, you just jumped the. Put HC2H3O2 on the top. Somewhere up there. HC2H3O2 and an arrow. I'm so glad you brought that up. Okay, watch.
That's acetic acid.
So watch. Didn't I say that acetates are always soluble? But also, focus, didn't I say that you must follow the rules in order?
Yeah.
So yes, if you get to the C rule, anything you put in front of acetate will 100% be soluble. However, if I look at this right here, isn't there an H sitting in the front of that?
But it's not.
So the rule has to be an A rule, right? So if I look at the A rules, the A rule says it has to be CBS pin to be soluble. Is that part of CBS pin? No, therefore it is insoluble. Are you guys with me here? Leo, I was actually literally going to do that first and then go to that. So thanks for like sharing my brain on that one. That is exactly what I would have done. Ooh, you got applause. Which makes me wonder why I don't get applause when I'm teaching, because I teach really well. No, I reject your applause right now. I reject it. I do remember there was a period of time, I did this for like literally like 2 weeks straight. I was just overwhelmed with everything. So I just told my students, you're gonna give me a standing ovation every single time. And then randomly throughout the lecture, when I teach really well, I would like a standing ovation. And I wish I'd filmed this because it was just really funny. Like I teach something and they just rise and just applaud. And it made me feel so good. And then I did this, we have, you know how you have community groups? So what we did at the school I was at, you had classroom groups that would go to meet things. So like my group would all be sitting together. So we would meet in this huge gymnasium. And I thought it was like great until I got really embarrassed. So I walk in the door and all my class stands up and gives me a standing ovation in front of like a whole like auditorium that was filled with everyone like looking at them like, what the heck? And I'm like, all right, you've proven your point. No more, you don't have to do standing ovations ever again. I like to think that I did it just because in their hearts they felt I deserved it. But anyway, that was something you didn't need to hear. If we look down at the very bottom here, so group 7, he put them all in there at the end perfectly. Fluorine, chlorine, bromine, iodine, and what is the bottom one there? Acetane. And then there's actually someone actually put the other class put like the UUN, which is ununceptium. What is it? Ununceptium. Yeah. Oh, super fun fact. They started doing that because when people were discovering, these are like man-made elements of things that they discover, and they exist for like thousandths of a second. And so people will discover the element, and they're like, I named it Johnstium. And they're like, no, you can't do that. And so they came up with this other number system. Although you'll see on some other previous periodic tables, you see like Berkelium because they discovered it at Berkeley. Okay, all of those are soluble. So you put anything with fluorine, chlorine, bromine, iodine, they're soluble, except for, I want you to write next to it, except for, so right to the right-hand side, right, soluble, except for Pb2 plus, right a little bit bigger there, Pb2 plus, Hg2 plus, and Ag plus. So if you ever see Pb2 plus Hg2, hey, rude child. Pb2 plus, Hg2 plus, or Ag plus in front of any halogen, they will be insoluble. They will hook up. That makes sense? Now, I will share with you the acronym that a young lady came up with. I always feel bashful doing it. I did not have a way because I didn't know how to attach them together. And she's like, oh, PMS. I'm like, PMS? Well, if you look at it, the P for the PB, M for mercury, S for silver. So if you think about it, anything of the halogens are always soluble except for PMS. If you want to come up with a different, hey, please feel free to come up with a different acronym. So I've used this for 15 years, and every time I'm like, ugh. But students remember, and then I see them like talking about, well, it's not part of PMS. I'm like, oh. So if you have PMS, Pb2 plus, Hg2 plus, or Ag plus with any of the halogens, those are insoluble. Everything else is soluble. So if you look at the NAGSAG rules, all of NAGSAG are soluble, but with some exceptions occasionally, with the S and the G. Let me hear it.
Yeah, I probably just forgot.
Okay, tell what it was, please.
Put hickeys away.
Okay, that almost seems more memorable. I don't know how you put a hickey away. Oh, so someone's doing it, like put that away. I don't know.
Just put like concealer.
Wow.
Hey,
You know, Adam.
if you want to do put hickeys away, go ahead. Or any other pH. In fact, you can vary the order, like maybe half or I don't know. So now here's the problem. Everyone focus. We're almost done. Okay. Here's the problem we face. So far with H, OH, and NAGSAG, do you realize we only have like a handful of ions? Like, what about all the other ions? What do we do with them? Well, there's a sweep up rule. So it's actually C part 2. And here's what we do. If none of the other rules can apply, we go to these rules right here. So I'm going to go again to our little Twilight Zone thing. Whee! And then we're going to go to this. And so this is part 1. So NAGSAG is part 1. And part 2 is -1, -2, and -3.
What?
Someone just turned on that.
My thing closed out. Oh, rip.
So, thank you for that. Okay. Can you write up there MgC2O4? Put it in the middle. Just right dead in the center. No, leave it underneath it. It's too beautiful to erase.
The one deeper color, the other right there.
I think Sam is volunteering to do it next task period.
No.
Because evidently he has the best ways to do
I
everything.
did very well the first time.
MgC2O4.
Yeah, I wanted to end on a high note.
Like drop the pen, like Mike. Yeah. All right. Coming back here, we're gonna go back to the board. Stop the horror. And back to him. Okay. So watch. What if I gave you MgC2O4? And I'm gonna do this rather quickly, but I want you to have your solubility rules kind of handy so you can look through them. Okay. If I looked at the rules, is there an A?
Yes. No.
No hydrogen. Is there a B? No OH minus. Let's look at NAGSAG. Isn't that the C rule? Is there a nitrate?
No.
Is there ammonium?
No.
Is there a group 1?
No.
How about sulfates?
No.
Acetates?
No.
Or group 7?
No.
None of them apply, right? So when nothing applies, here's the trick. We go to the negative ion. Put your finger on the C2O4. What charge does C2O4 have? Has a 2 minus. If the charge on the negative ion is a 2 minus or a 3 minus, insoluble. If it's a plus, or if it's a negative one, it is soluble. So in this case, wouldn't this be insoluble? Which means that if I threw that MgC2O4 into water, it would not dissolve to begin with. But if I brought Mg2 plus and C2O4 independently together, they would hook up. Are you with me? Okay. There was a worksheet that was on one of the tables here. Can someone, where is it? No, there's actually, it was from the last class period. Yes, is that it? All right, can everyone grab one of those?
Everybody grab one of these.
And then can we put it on the edge of the table over there? It's right there.
It's gonna be so much fun to do.
I feel bad for embarrassing you.
Are we gonna get a test back?
I'll put them on the portal. Okay. Let me show you. I'm going to screen share my screen for just a second. You guys are seeing me, I hope. Okay, let me show you something here really fast.
Guess I can't do my homework.
Okay, watch. Children and grown-ups alike. If you go to second semester and then under net ionic reactions, can you guys see on the screen? Under notes, I've included the PowerPoint, but then I also, this is what, there's two things that are going to be your homework for tonight. First thing is you're going to create a solubility rules yourself. This is actually the original solubility rules this young lady, Sam Norland, did. She actually put this together from my SAWS thing. And she changed it, like everyone else came up with a SAWS table, because that's how I was teaching it before. And it was, SAWS was strong acid, aqueous compounds, weirdos, and strong bases. And it was not following the ABCD order. By the way, notice how we didn't talk about D? D is different. Thank you. We don't need to know it right now at this level. But what I want you to do is I want you to put together on one single sheet your version of this. You cannot copy and paste, but you want to do it. I would include different on there because down the road you may need it, particularly if you take AP chemistry, which I hope you all will be considering. But this is how she put them together. I'm okay with not seeing any more people with their pants sagging as the SAG rule, because I saw so many of those from previous classes. But if you feel you must, you have a particularly good one, have at it. This is your homework, is to put together pretty rules. Now,
Do we have to like organize them in our own way?
it can be the same way if you want to, but I just want to have your own little touch.
Okay.
Now, let's go to the worksheets here. And the worksheet we're going to do right now is a solubility problems one. So, yes, ma'am.
Does it have to be online or can it be?
I would like to have it be online. That way I want it online. Although I know that some of you guys are super artistic and they probably do a better job without it, but all right. Can you guys see me moving around here on the screen? Okay. So let's take a look at Ag2SO4. And the question simply is this: is that soluble or is it insoluble? Now, if we're going through this, do you realize that we're going to kind of go through the rules and see which one hits first? So let's start off here. And let's actually start in the front of the room. Maddie, you're going to start off. Tell me the first rule with A and tell me if it applies. Why not? No H. Next. No, it doesn't. But why is it not a B? No OH. Now let's go to the C rules, right? Now we start jumping with NAGSAG. Let's do one H here. Caitlin, is there an N?
No.
No. Up front here, Adam, is there an A?
No.
Why not?
Huh?
What's an A stand for?
Ammonium.
Ammonium. No ammonium. Reagan? You kidding? Well, that went by fast. All right. So your homework is this. I'm not going to make you do this worksheet right now. Keep it for next class period. Okay. Your homework is going to be learn the rules. So I'm going to make it a way for you to show me if you've learned the rules. So make a good page of it and then learn the rules.
So no worksheet
No worksheet homework.
I have a question.
Hold on one second. Let me just cut off the podcast.